Before we can start looking at infinitely repeated games, we need to understand how we would evaluate the payoffs you would get in an infinite game. Remember, you're going to get a payoff in each period from the stage game that's played in each period, and your total payoff, which sometimes we'll refer to as the lifetime payoff. So your total payoff is the sum of the payoff that you get in each period. We refer to these payoffs that you get, one in each period, as a stream of payoffs. And we need to first be able to evaluate such streams of payoffs before we can analyze infinitely repeated games. After all, if there's one strategy that gives you a payoff of 1 in every period, another strategy that gives you a payoff of 2 in every period, the first one, if we simply just added up the payoffs you get in every period, if we add 1 infinitely many times, we get infinity. If we add 2 infinitely many times, we get infinity, and we can't really compare those two things. So we're going to use the idea of discounting to calculate essentially the net present value of the stream of payoffs. So let's say you have a stream of payoffs. So you're going to get a payoff in every period. So we'll represent time along this arrow, and it goes in this direction, to the right. So you get a payoff in period 1, you get a payoff in period 2, in period 3. In general, you're going to get payoff in period t. And this is true for every possible t. There are infinitely many periods, and you're going to get a payoff in each one of them. Just to keep things simple, since we're trying to understand how we evaluate these streams of payoffs, let's suppose the stream of payoff is the simplest one, where you just get 1 in every period. So you get a payoff of 1 in period 1, you get a payoff of 1 in period 2, a payoff of 1 in period 3, and so forth in every single period. Let's suppose your discount factor is delta. Then your first period payoff, 1, from today's perspective, it's worth 1. So the current value of the first period payoff in the first period is 1. What's the value of the second period payoff in the first period? We discount future payoff by delta per period. So it's delta times 1. The third period payoff is delta squared times 1, because from the perspective of period 2, the third period payoff would be worth delta times 1. And so from the first period payoff, that delta 1 is worth delta times delta 1, which is delta squared 1. In general, the payoff of 1 in period t is worth delta to the t minus 1 times 1. So the total value you get, which we'll represent by the little v, is 1 plus delta squared plus delta cubed. In general, the tth term is going to be delta to the t minus 1. So when we want to know what v is, now there's a convenient way we can write v. We don't have to express it as an infinite sum. If we look at the terms except for the first term, we can write this as 1, and then we can just factor out delta from the remaining terms. We get delta times 1 plus delta squared, and so forth. Inside these brackets, you have infinitely many terms, but this thing right here is just v. So we find that v is 1 plus delta v. That means v minus delta v equals 1, which in turn implies that v equals 1 over 1 minus delta. Now that's when you get a payoff of 1 in every single period, your total payoff is going to be 1 over 1 minus delta. In general, if you get a payoff of a in every period, that's going to be worth a over 1 minus delta from the perspective of period 1. Okay, so that's how we are going to evaluate these streams of payoffs. Now on to infinitely repeated games. We're going to play the same stage game in every period, and we're going to do that infinitely many times. As we saw with the 2-period game, a strategy has to tell us what you do in every information set, and that can become quite complicated for these repeated games. It was complicated enough when we just had 2 periods, but now when you have infinitely many periods, these objects become quite complicated. So a strategy maps a set of all possible histories. So take any history of play. For any t, look at all the possible action profiles that the players could have played in the first t minus 1 periods. That forms a history. And for any such history, a strategy has to tell us which action a player should play in the tth period. Now this set here, the set of all possible histories, is a very large set. Because remember, there are many histories, especially as t gets larger. And each history corresponds to an information set. So these objects can be very complicated just because they're mapping a very large set to the set of actions. So we need to be able to say for this very large set of histories, for every single one of them, what the player should do. And that can be very complicated. But rather than looking at all possible strategies, we can actually do a lot with some very simple strategies. And I'll give you some examples of these simple strategies. But before I do that, I want to make sure that we are clear that when we talk about an equilibrium and we talk about a player deviating to a different strategy, we're not restricting ourselves to only these simple strategies. We still have to make sure a player can benefit by deviating to perhaps a more complicated strategy. But we can still find equilibria that we're interested in, as we'll see later, that just involve these relatively simple strategies. So what are the kinds of simple strategies we might be interested in? One example of such a simple strategy is for each period t to designate an action for player I and say, play that strategy in period t. And you do that no matter what the history is. So by ignoring the history, you can simplify the strategy. The complicated strategies are ones where you are history dependent. Another example of a relatively simple strategy is one that says, play the action a bar I as long as the history only involves everybody playing the profile a bar. If at any point in the history, action profile that was played is different from a bar, play bi. That's one example of a strategy. These are actually called trigger strategies. It's called a trigger strategy because as soon as somebody plays something different from a bar, it triggers a switch from a bar to some other action b. This is a history-dependent strategy because what you play in period t depends on the history. Whereas in these types of strategies, what you played didn't depend on the history. You just play the strategy designated for that period. Now it could be that periods 1 and 2, the same strategy is played. That's fine. That would be one possible strategy. But the action that you're prescribed to play is independent of the history. Whereas this latter type of strategy is not independent of the history, it's dependent on the history. But this is dependent on the history in a very specific way. It says, as soon as somebody switches from a bar, you also switch from a bar to b. Otherwise, you stick to a bar. So these are just a couple of types of strategies that we could play, and they're relatively simple to describe. Note that you can use these types of strategies, the first type, to string together a sequence of stage game Nash equilibria. So, for example, for each period t, you pick a Nash equilibrium of the stage game, and you pick strategies for every player such that everybody plays in period t the Nash equilibrium of the stage game that you want played in period t, and you do that for every period. Then you can string together sequences of stage game Nash equilibria to form a subgame perfect equilibrium of the whole game. And we've seen this earlier for the finitely repeated games. But you can use these trigger strategies to do more interesting things, like supporting profiles of actions that aren't stage game Nash equilibria. So you can have players play profiles of actions that are not Nash equilibria in the stage game by using these trigger strategies. And we'll look at the Prisoner's Dilemma game to demonstrate an example of how you can do that. This is the Prisoner's Dilemma game that we've seen earlier, and there's a unique Nash equilibrium to this stage game. In fact, that Nash equilibrium is the strictly dominant strategy for each player. So for both players to play D is a unique stage game Nash equilibrium. So let's suppose the players play this game repeatedly, infinitely many times. We'll see that the dynamics change quite significantly from our analysis of this game as a one-shot game. So let me give you an example of a trigger strategy that can support cooperation as the equilibrium. So the strategy for player I is to play C in any period as long as the previous stage game outcomes were always C. Otherwise, play D. So what is this strategy telling us? It says, as long as the other guy cooperated with you in all previous periods, you play C. If he even once didn't cooperate with you, then you play D. This strategy is called the Grim Trigger strategy because in the Prisoner's Dilemma, it has the players cooperating, but as soon as there's any breakdown to the cooperation, there's no forgiving. We go to the non-cooperative outcome forever. There's no coming back from it. Now, it's a bit beyond the scope of this course, but it turns out that there are actually less punishing strategies you could use, but we won't get into those details here. But in this Prisoner's Dilemma, we call this the Grim Trigger strategy because as soon as there's any breakdown to cooperation, you never forgive the person. You always stop cooperating with them. And when you stop cooperating with them, you fall back to the stage game Nash equilibrium strategy. And so if you're playing the stage game Nash equilibrium action, your opponent is also going to have to play the stage game Nash equilibrium action. And so that's going to be an equilibrium going forward. So what's interesting is that this strategy of saying, look, we'll cooperate until one of us cheats. As soon as one of us cheats, we'll stop cooperating forever. This is actually a subgame perfect equilibrium. So let's verify that indeed that this is actually a subgame perfect equilibrium. We're going to use the one-shot deviation principle to do that. we're going to express player I's payoff in period T in two parts. The first part is their payoff from period T, and the second part is the discounted continuation value. So in period T, from the perspective of player I, sitting at the information set at period T, when they look forward down the game tree, their payoff is going to consist of the payoff they're going to get from period T itself, plus the continuation value they're going to get starting at period T plus 1, but we're going to have to multiply that by delta in order to be able to compare today's payoff, today being period T, and tomorrow's payoff, tomorrow being T plus 1. So if we want to convert utility of tomorrow into utility of today, we multiply it by the discount factor. And then we can add it to utility of today, which is ui of t. So we're going to use the one-shot deviation principle to check that neither of the players has an incentive to deviate, no matter what the history is. So all we have to check is that deviating from the Grim Trigger strategy is never beneficial after any history in a given period. So let's start with the history where somebody has played something other than C, and so Grim Trigger tells you to play D. So would either of the players benefit from disobeying the strategy? Since Grim Trigger says to play D, the payoff you get from playing D is your current period payoff is going to be 1 because the other player is going to play D as well, because the Grim Trigger says that you should be playing D. Because Grim Trigger says to play D forever, both players are going to play D forever, and so they're always going to get 1. Starting tomorrow, they're always going to get 1, so the lifetime payoff starting tomorrow is 1 over 1 minus delta. Your payoff from playing C is your current period payoff would drop to 0, because remember, if you play C and the other guy plays D, and Grim Trigger tells the other guy to play D, the other guy gets 3, but you get 0. So you get 0. But you don't change the continuation payoff because Grim Trigger is going to tell you tomorrow to play D again. And remember, we're only looking at a one-shot deviation. So starting tomorrow, you're going to go back to obeying the Grim Trigger strategy. So you get the same continuation value. So your continuation payoff is the same. By disobeying the Grim Trigger strategy today, you have not changed your continuation payoff, but you have decreased your payoff today. So deviating from D to C isn't beneficial. You're only going to reduce your payoff. So there is no one-shot deviation following a history where somebody has played something other than C and Grim Trigger is telling you to play D. What about after a history where only CC has been played in all periods? Following such a history, Grim Trigger tells you to play C because nobody has played D ever, so you should continue to play C. So your payoff from sticking to C and obeying the Grim Trigger strategy is that in this period you're going to get 2. And your continuation value is going to be, you're going to get 2 in every period, so you're going to get 2 over 1 minus delta. So your total lifetime payoff from here forward is 2 plus delta times 2 over 1 minus delta. Remember, the total payoff is your utility from today plus delta times your continuation value. The payoff you get from playing D, well, today you're going to get a bump in your payoff. The other guy is playing C, and if you play D, you get 3. So you get a bump to your payoff today. However, you're going to pay for that because in the future, Grim Trigger says both of you should just play D and you're going to both adhere to that. So you're going to decrease by cheating today your continuation value to 1 over 1 minus delta. So when we add those up, your utility today plus delta times your continuation value, your total is going to be 3 plus delta times 1 over 1 minus delta. So deviating is not beneficial if and only if the payoff you get from not deviating is at least as high as the payoff you get from deviating. If we simplify this, it's 2 minus 2 delta plus 2 delta divided by 1 minus delta. The minus 2 delta and the plus 2 delta cancel, so you get 2 over 1 minus delta is at least as big as 3 minus 2 delta divided by 1 minus delta. Since we have the same denominator, if and only if 2 is at least as big as 3 minus 2 delta, which in turn happens if and only if 2 delta is at least 1, which happens if and only if delta is at least a half. So as long as delta is at least a half, deviating from C to D following such a history would not be beneficial. So what we've seen then is that as long as delta is greater than a half, it is a subgame perfect equilibrium for both of these players to play the Grim Trigger strategy. The story that this subgame perfect equilibrium tells is that CC is the cooperative outcome that the players would like to achieve. Remember, it's the Pareto efficient outcome in the stage game. But they can't achieve that when they play this game only one time. Even if they repeat it only finitely many times, they can't achieve that. But when they play this game infinitely many times, they can use DD in the stage game as a way to punish one another for breaking the cooperation. So even though CC is not a Nash equilibrium of the stage game, they can support CC by threatening to punish one another by switching to DD. You could think of it also in sort of a converse way, where they can reward each other for playing CC by continuing to play CC, and once they don't play CC anymore, they can switch back to what could be achieved had there not been repetition. And it's this quote-unquote shadow of the future, as Axelrod called it, that allows the players the opportunity to either reward or punish one another for current actions in the future. That's why the analysis of the one-shot game is fundamentally different from the analysis of the repeated game. This actually often explains why when you have players play in an experimental lab, for example, when you have people play a one-shot game, we're all very accustomed to playing games interacting with one another in repeated manners. So a lot of times we can be biased towards playing a more cooperative outcome because we're attuned to thinking of games as being repeated and not as being one-shot games. Now, the analysis we've done here is quite general. It doesn't apply only to the Prisoner's Dilemma game. It applies more generally to what are called mixed motives games, games where there's scope for cooperation, but where cooperation doesn't necessarily happen in the stage game Nash equilibria. We can support Pareto improvements in the repeated version of the game. Typically, the ingredients needed: a utility level for each player from cooperating, the highest utility you could get from deviating, because there might be more than one deviation. In this Prisoner's Dilemma, there's just the one deviation, but you could think of a more complex game where there's potentially many ways to deviate, and you would look at the highest possible deviation payoff. And we need a punishment payoff, where the punishment has to be a stage game Nash equilibrium. So in our example, UIC was 2, UID, so the payoff you get from deviating from cooperation, was 3, and the punishment payoff was the stage game Nash equilibrium payoff, which is 1. So the gain from deviation is the payoff you get from deviating minus the payoff you get from cooperating. That comes at a cost. The cost is that you're sacrificing future payoff, because the future payoff is going to drop from the cooperation payoff to the punishment payoff. You would have gotten UIC in every future period, so your continuation value would have been UIC divided by 1 minus delta, so your discounted continuation payoff would be delta times that. But if you deviate, you get the punishment payoff in all future periods, so your discounted continuation payoff is delta times UIP divided by 1 minus delta. So that's delta times UIC minus UIP divided by 1 minus delta. So as long as the gain from deviating is no greater than the cost of deviating, you won't deviate, so Grimm trigger would form a subgame perfect equilibrium. If you solve for a condition on delta, I'll walk you through the math. UID minus UIC, so we'll cross multiply by 1 minus delta UID plus delta UIC less than or equal to delta UIC minus delta UIP. This guy and this guy cancel, so that's equivalent to UID minus UIC less than or equal to delta UID minus delta UIP. Factoring out the deltas, so as long as delta is at least as large as the ratio of UID minus UIC to UID minus UIP, then the Grimm trigger strategy is going to be a subgame perfect equilibrium. So as long as delta is big enough, Grimm trigger strategies work. Now, Grimm trigger strategies give you a way to support a specific action profile in every period. In the next video, I'll show you how you can actually do more complicated and more interesting things. And we'll actually get a better understanding of all the things you can achieve, because you can do more than just this.